Greetings everybody. This is the second video for the Chapter 8 Lecture Notes Part 1. And this is going to deal with impulse, momentum and impulse. Well, remember, in the previous lecture we looked at conservation of momentum. If the sum of the external forces acting on the system equals 0, then the initial momentum of the system, pi, equals the final momentum of the system, pf. And we did the example with the archer firing the arrow, where we know that momentum is conserved in the x direction because there are no external forces acting on either the archer or the arrow in the x direction. There are no forces acting on either object in the x direction because neglecting air resistance and the ice is frictionless. So momentum's conserved in the x direction. And we set it up again. Initial, that's before he fires the arrow. Final is after he fires the arrow. M2 is the arrow, M1 is the archer. And then apply conservation of momentum. And we're looking for V1 final, the velocity that the archer moves across the ice after firing the arrow. Okay, now a question would be, okay, momentum's conserved if there are no external forces acting on the system. But remember, when we say that, the qualifier is, you can remember momentum's a vector. So we mean in a specific direction. For example, momentum can be conserved in the x direction, but not the y direction, or vice versa. Okay, so we have to, when we say that, we're saying, specific direction. However, what if there is an external force on the system? Meaning, what if this condition does not hold? Well, that's okay. We can deal with that. That means that the momentum of the system will change, so pi will not equal pf. Well, let's rearrange Newton's second law. Remember, we wrote that Newton's second law in terms of momentum. F net is equal to delta p over delta t. Well, let's rewrite this. Let's solve for delta p. Because remember, we're now dealing with the fact, what if there is an external force on the system? So this qualifier no longer holds. The sum of the external forces equals 0. It's not that case. But what if there is an external force? Well, we can deal with its impulse. So now rearrange Newton's second law. The net force, F net, is delta P over delta T, meaning delta P is F net delta T, right here, delta P. Well, we define the impulse of the system. We define impulse to be change in momentum, delta P. And we use an uppercase I to indicate impulse. Some of the literature uses a J, but most use an I for impulse. So delta P is F net delta T. Well, we define the impulse to be delta P, the change in momentum. Well, what is the change in momentum? Well, it's M V final minus V initial. Right here. What is delta P? Delta P is M V final minus V initial. Okay? Well, so I is equal to delta P, which is M V final minus V initial. Well, what is delta P? We know delta P is F net delta T. Those are the impulse equations. I is equal to delta P, which is equal to M Vf minus Vi, which is equal to F net delta T. Well, the units of impulse are the same as the units of momentum, kilogram meter per second, but also impulse can also be, because it's force times time, it's also a Newton times a second. And if you happen to graph F versus T, and what happens is, with an impulse, why do we have like a Ti and a Tf? Well, what happens is an impulse is exerted on an object. You need to have, remember, we're dealing with the case where F net does not equal 0. In other words, there is an external force. Well, typically, some examples of impulse would be, what if you hit a golf ball off a tee? Well, the club. So you swing your golf. I hate golf, by the way, but it's in terms of physics, it's a good example. So you have a golf ball resting on a golf tee. So you hit it with the club. Well, the club, we say in the language of physics, the club is exerting a force on the golf ball. That's your force. The club is exerting a force on the golf ball. The club and the golf ball are in contact for a time interval we call delta t, or sometimes just t. So what happens is T initial, that's when the golf club initially encounters the golf ball. Then what happens is, when the club actually strikes the ball, the force it exerts on the ball increases, and the ball actually gets deformed, it gets compressed. Then what happens is that force increases, force club on ball increasing, golf ball's getting compressed, getting deformed. Then at the maximum compression, then the golf ball is now going to decompress back to its original shape. As it's decompressing, it's still in contact with the club, but it's beginning to decompress back to its original shape. And right there at T final, that's when the golf ball actually loses contact with the club and flies off the tee. And so impulse is also equal to the area under the force versus time curve. And typically the F versus T curve is going to have this peak. Well, we typically take an average. We draw this rectangle from Ti to Tf. And the height of the width, so that's the width of the rectangle, is from Ti to Tf. The height of the rectangle is the average force exerted, in this case exerted by the club on the ball. And typically that average force is half of this peak. That's how I knew how to get the height of that rectangle. So the width is given by, you start at Ti, go up to half the peak, then go over, then go down to Tf. And so the area of that rectangle is equal to the impulse. So impulse is equal to the area under the F versus T curve. Let me pause this for a second. Well, so what does this mean again? When I say, I was using the example of the golf club hitting a golf ball. Let's look at maybe a little easier example. Let's look at somebody kicking a soccer ball. And what does that mean? Well, here, let me bring up a video. So and the idea is that T initial, that's when the foot and the soccer ball initially make contact, and then the force exerted on the soccer ball is increasing. When you hit the max force, the soccer ball has been deformed, been compressed to its maximum compression. Then the soccer ball is beginning to decompress back to its original shape, decompressing, but it's still touching the foot, decompressing. Then at T final, that's when the soccer ball loses contact with the foot and flies across the soccer field. So let's go ahead and look at that. And see here's your soccer ball. And
I'm going to show you an example of the type of problem we'll look at in this chapter. I have this toy gun here, and so if you kick the force as a function of time as she kicks the ball, it looks like this. It rises to a maximum and then drops back down to 0. Now can be a very, very complicated force equation. It can be a very, very complicated force graph. I'm interested in the force on the ball, and it's a large force. And you can see the amount that the ball is deformed starts out small.
Right there, that's your Ti. That's when the foot first makes contact with the ball. Notice the ball will begin to get deformed.
Small.
See that?
Gets bigger and then decreases again. If we were to draw a graph up,
and then that's when the ball will lose contact with the foot.
Again.
And it goes back to its
if we were to draw
shape.
A graph of the force as a function,
and that's what we mean. That's what's going on.
Of time as she kicks the ball, it looks like this. It rises to a maximum and then drops back down to 0. Now can be a very, very complicated force equation. It can be very, very...
And that's what's happening. In other words, TI is when the foot first makes contact with the soccer ball, and that force is increasing. The soccer ball is getting compressed. Then when the force reaches its maximum, the soccer ball is going to begin to decompress back to its original shape. But it's touching the foot until it leaves at T final. And typically the average force, you take this peak, remember it's F versus T, half of the peak is the average force. And then the area under the F versus T curve, that's the impulse. But that's where the origin of that graph comes from. This little video right here.
Increases again. If we were to draw a graph of the force as a function of time as she kicks the ball, it looks like this.
Right,
it rises to a maximum and then drops back down to 0.
And then it leaves. Yep.
Now
and again, the same principle holds. I wish I'd saved that video. The same principle holds. Think of, she was kicking the soccer ball with her foot. Well, again, you could be hitting a golf ball with a golf club, hitting a baseball with a baseball bat. But in that case, her foot is applying an impulse, is exerting a force on the ball. It's imparting an impulse to the soccer ball. A baseball bat imparts an impulse to a baseball. A golf club imparts an impulse to a golf ball. But the physical situation is always the same. An impulse is equal to I is equal to delta P, which is equal to M, VF minus VI, which is equal to net force delta T. Or sometimes with impulse, typically with the net force, we really talk about the average force, which you just take the peak of that F versus T curve. Half the peak is the average force. And then you form your rectangle. You go from TI, average force, over, then to TF and down. And the area of that rectangle is the impulse. The area under the F versus T graph is the impulse. And let me go ahead and do just a couple of what I call quick quizzes, and then in another video I'll throw in some numbers. So here you have a dashboard, seatbelt, and airbag. They're each used separately. They're each used alone in separate collisions. The crash test dummy type stuff. And in each collision, they have the same speed. So whether you're testing a dashboard, seatbelt, or airbag, you're testing them all from the same initial speed. Well, in terms of impulse, rank them from greatest to least. Well, the impulse is the same because they're going from the same initial speed to a full stop, obviously. Collisions meaning the car collides and stops. So in each case, the initial speed and final speed are the same, and so the change in momentum is the same. It doesn't matter what stops the passenger, whether it's dashboard, seatbelt, or airbag, they're starting from the same speed, and because of the collision, obviously, they're brought to a rest. So the impulse is the same in each case. Now what happens is we'll find out that the airbag exerts the smallest force on the passenger, and hence has the, so hence it does the least damage. Okay, and we'll finish up with quick quiz part 2. Same example. We know that the impulse is the same in each case, but what about the average force exerted on the passenger? Which one exerts the greatest force? Dashboard, seatbelt, or airbag? Well, obviously, dashboard exerts the greatest force, then the seatbelt, then the airbag. Well, why? Well, if I is equal to F delta T, F is equal to I divided by delta T. So the impulse is the same. We know that from quick quiz number 1, because in each collision, the passenger is starting from the same speed, and it's a collision, so they're coming to a full stop. So the impulse of the passenger is the same in each case. But but the delta T, the time it takes for the passenger to come to a stop, well, that's going to be delta T is greatest for the greatest for the airbag, middle for the seatbelt, and delta T is shortest for the dashboard. So dashboard will exert the largest average force, then the seatbelt, the airbag will exert the least amount of force because the airbag allows you to stop in the largest time delta T. And that's why, yeah. Yeah. Because again, and the converse, the smallest delta T results in the largest average force. Think about, God forbid, the passenger, if the dashboard, God forbid, if you run into drive into a tree or a wall, without an airbag, your head's going to slam into the dashboard in a relatively very small delta T. Or if the airbag deploys, you can sink into the airbag and you come to a stop in a much longer delta T. So dashboard exerts the largest force on you, which will do the damage. The force is what does the damage. So that's why airbag is the least amount of force and it does the least amount of damage. But again, think about that video of the girl kicking the soccer ball, and I think that explains this graph pretty well. Okay, let me go ahead and stop this video, and the next one we'll actually do the numbers.